In this video, we're going to develop the solution method for Bernoulli's equation. So in the previous video, we saw that Bernoulli's equation has this form, dy dx plus p of xy equals f of xy to the n. And in particular, we said we're going to be interested in Bernoulli's equation for the cases where n isn't 0 or 1, because these two cases reduce to something for which we already have a solution process. So we're going to focus on the case where we have a nonlinear equation here. And the idea is, for the first step, what we do is multiply both sides by y to the negative n. And if we do that, then we have y, the base y to the n times base y to the negative n. So we get to add the exponents. We get y to the 0. And as long as y isn't equal to 0, for y not equal to 0, then that gives us a 1 here. So the right-hand side, when y isn't 0, reduces to f of x. And if I distribute, now I can distribute the y to the negative n in. So I get dy dx y to the negative n plus p of x times, and y to the negative n times y to the first is just going to be y to the 1 minus n. And the idea is we want to try to linearize this equation. We have, if n isn't 0 or 1, we have a nonlinear first order differential equation. We'd like to linearize it. So what we do is make the substitution w, which is w to the first, which is a linear term. We substitute w equals y to the 1 minus n. And then what we need to do is figure out what dy dx is if we make this substitution. So I'm going to do dw dy equals, we'll take the derivative with respect to y of both sides. So we get the exponent 1 minus n comes down. We get y to the, we subtract 1 from the exponent, which is going to be 1 minus n minus 1, which is just negative n. And then what we want to get is dw dx, which we can replace with just y prime, if, w prime if we want to. So I'm going to need to multiply by dy dx. And I take the derivative of y with respect to x, so I do dy dx, and dw dy times dy dx is just dw dx equals, and then what I can do is divide both sides by 1 minus n. So I'm going to get a 1 over 1 minus n on the left hand side, and that's going to leave me with a y to the negative n times dy dx on the right hand side. So this guy is important, and this guy's important, and we're going to go over here and make some substitutions. So dy dx times y to the negative n, dy dx times y to the negative n can be replaced with 1 over 1 minus n dw dx. Okay, so we can replace that with 1 over 1 minus n dw dx, which we'll just call w prime, plus p of x times y to the 1 minus n, but y to the 1 minus n can now be replaced with a w, and this equals f of x. So at this point, I've linearized this. I can multiply through by 1 minus n, which will give me w prime plus 1 minus n times p of xw equals f of x times 1 minus n. And what I want to notice is that if I let little p of x equal 1 minus n bit times big P of x, and I let q of x equal 1 minus n right here times f of x. So if I just rename those terms, I now have an equation that looks like w prime plus p of xw equals q of x, and this you should recognize as the form of a first order linear differential equation from the previous homework assignment. And we can solve this equation by using the integrating factor u equals e to the antiderivative of p of x dx. So that's going to be the general solution process. We're going to multiply both sides by the y to the negative n, and then we're going to make a substitution here, w equals y to the 1 minus n, and the idea is to linearize the differential equation. We're trying to take a nonlinear first order ordinary differential equation and rewrite it via a substitution as a first order linear differential equation for which we can solve using an integrating factor.